In this video I built my second ever model, a smart parachute system that detects when it's falling and automatically deploys mid-air. Nice. Okay, I think it's good and we can go outside and give it a try. After 8 successful launches, everything was working perfectly, until launch number 9, where just one line of code could have saved the entire model. This is a full journey, from planning and collecting flight data to testing, manufacturing, and finally launching the model. The project sounds simple at first. I throw the model into the air, it goes up, reaches the highest point, and when it starts falling back down, then I deploy the parachute. I was already working on an autopilot for my RC car. That system used an accelerometer and a gyroscope to keep the vehicle pointed in a set direction. So naturally I thought the accelerometer could solve this problem too. If it can sense the motion irritation, maybe I can detect when the exact moment happens when the upward motion turns into a free fall. To test the idea, I built a quick prototype on a breadboard using a Raspberry Pico, MPU 6050 and a USB battery pack. Then I wrapped the whole thing in several t-shirts like a burrito, so I could throw it indoors without destroying it in day one. The plan was simple: collect real flight data, study the graphs, and see if the accelerometer could tell me when to fire the parachute. So this is all the data I've collected from one of the throws. This column represents time from the moment when Pico was powered up, and these three values represent accelerometer data, and these three represent the gyroscope. This column has a formula to calculate overall acceleration on the model. It's a square root of squares for each of the axes of the accelerometer. So if we're going to plot them, we're going to see how it behaves. And we can see how I'm throwing the model up, and we see all the data here. Then I tried similar throw, but I was rotating everything around. And rotation itself also adds to accelerometer readings, and as a result the signal becomes very noisy. So I start exploring what are my options to actually go and find the moment when I need to deploy the parachute. And after looking around, I actually realized that accelerometer is not going to help me at all. So I went back to basics and read about free fall. In physics, free fall means that object is moving only under gravity. That starts the moment it leaves my hand, even while it's still going upward. Then it slows down, stops, and comes back down, but the whole time is in the free fall. Free fall is not the same as falling downward. It includes both climb and descent. Then I checked the accelerometer article, which confirmed the same thing. The reading is 0 while the object is under free fall. So I needed a different way to detect the top of the trajectory. I had two options. One was to estimate how hard through the model and then calculate when it should start falling based on gravity. And the other was to measure altitude directly with a pressure sensor, which I already had. After I assembled the model and added pressure sensor and did another throw, this data I collected. The blue represents the accelerometer data and the red represents the altitude. So I basically start at roughly 124, there is a bit of noise, I throw it up, and you can see that the data for the accelerometer does not help me to detect the moment when the object is on the top of the trajectory. But accelerometer did show me the peak, and I can eliminate the noise with a filter, so that's the direction I decided to take. Once the sensing problem was solved, it was time to design the model in FreeCAD. I split design into three main sections: the power, the logic, and the release mechanism. I powered the system with 3 AAA batteries. This way I keep the weight of the system lower, and also these batteries are much more crash resistant. The middle section contains the electronics. This is where the Raspberry Pico and both sensors live. I put them in the middle so they had better chances to survive should a crash happen. The parachute release section contains a servo and a pin, and when the brain detects we are going down, the pin is being pulled in, which releases the parachute. I've started with the power section and 3D printed the battery frame. This part is simple, but it has to be reliable, because everything else depends on it. Next, I mounted a physical switch so I could turn the whole system on and off without disconnecting batteries every time. A small detail, but it makes testing much easier. For the battery contacts, I use a strip of brass, and before cutting anything, I checked with a multimeter to make sure it was conductive. Then I cut brass into small pieces and shaped them into contacts for the batteries. I put a little bit of elastic behind to add a little bit of spring. Exactly what I wanted, and the power module was ready for the next stage. I printed a dedicated frame to hold the Raspberry Pico and both sensors in place, then mounted everything with screws so the components would stay secure during launches and impacts. Once the hardware was mounted, the next step was wiring it all together. I like to sketch its connections first before touching any wires. It's much easier to fix mistakes on paper than after soldering. So here I mapped out the full layout, power lines, ground, and the signal connections from Pico to each sensor. The final section was the parachute release mechanism. I mounted a servo inside the top frame, then I installed a locking pin that physically holds the parachute closed during the launch. Mechanically, this was one of the most critical parts of the whole project. If it sticks, jams, or releases early, the flight is over. And while I'm building the section, I made a small mechanical mistake that ended up cancelling the very first launch attempt. I didn't know it yet at this stage, but I'll come back to that problem later in the video. With all three modules finished, it was time to assemble the full device. For the electronics module, I used rubber bands to hold it in place instead of mounting with screws. The idea was to reduce the shock to the sensors to the controller when model lands. Alright, and this is fully assembled device. So I turned it on, connected to my computer. There is a light there saying we are working, and we can give it a shot on ARM. So I'm gonna go into the application and click ARM. And the application is armed, and we can see our ground and all the data on the screen. I'm gonna lift it up and I hope you get it. 0.6 seconds to do this. Okay, so that generally makes the device up and running. We can switch to the parachute. With the weight known, I was able to calculate the size of the parachute. The rule of thumb is to check a square root out of the weight and multiply that number by 5. This gave me roughly 80 cm size for my parachute, and the spill hole should be 10% of the hole size. I decided to use a garbage bag, and here is how you can create a shape with 8 attachment points. I use an electric tape to attach all the lines to the parachute to make sure nothing is going to be ripped off on launch. In addition to the code which runs on the Raspberry Pico, I also created an application which is based on React.js, and it runs in Google Chrome and controls the device over the Bluetooth. It supports options like recording data, showing live data from all the sensors, or I can arm the device when it's ready to get started. I'll talk about the algorithm behind the ARM when we get to the first semi-successful launch. Before launching it outside, I wanted a safe way to test the altitude sensor at home. My first idea was to use a plastic container connected to a bike pump, so I could change the air pressure and simulate the model going up and down. That was a decent plan, except that the model did not fit into the container. So I moved to a simpler solution, a regular plastic bag. By squeezing and releasing it with my hand, I could change the pressure around the sensor. Less pressure simulates climbing, and adding pressure back simulates descending. It looked a bit ridiculous, but it gave me a quick way to test the system indoors. Okay, we're going to add pressure. 172, we're going to arm it. We're going to let pressure go, and coming back. Awesome. To keep the parachute packed during a launch, I use a simple rubber band. The band stretches over the parachute and it is held in place by the release pin. And before heading outside for real launch testing, I wanted to test the parachute on its own. So I used a hockey puck and a few coins to match the weight of the model as closely as I could. This gave me a simple test mess, without eating the electronics or the frame. My first field test started with the parachute alone. Before risking the full model, I threw the dummy away several times to see how the parachute would deploy and how well it slowed the descent. Then I attached the parachute to the full model and armed the system. Before attempting a real launch, I decided to do one last low-risk test. Just toss it about a meter into the air and catch it. Honestly, the great decision. I clearly heard the servo activate, which meant the electronics and the software had done their job, but the parachute never deployed. This isn't the mechanical issue I mentioned earlier. The connection between the servo and the arm, the release pin, was too weak. Once the parachute was packed, the rubber band added extra tension, which pushed the pin against the housing. When the servo tried to pull it free, the linkage slipped instead of releasing the lock. So the logic worked, the servo worked, and the parachute still stayed trapped inside. At that point, there was nothing to launch, so I packed everything and went home to redesign that mechanism. Since I did not have a screw to fit into the arm of the servo, I used a thin wire as a connector, and clearly that was a big problem. But now when I know the issue is, it was a relatively straightforward fix. I basically was able to fit a continuous wire and add a tension screw on one side, which allowed me to create a very solid connection. And then I went outside to give it a try. Unfortunately, I forgot to turn on the camera, so here is the picture of the first launch of the model. So here is what happened during the first flight. That was the original plan, to deploy the parachute on the top. But what actually happened, the parachute was deployed way late, and it was so close to the ground that it did not have enough time to actually engage. And I decided to understand how did it work. There are two variables in the code on the microcontroller itself, the current altitude and the watermark altitude. This is pretty much the highest altitude we've seen so far. And as soon as we see the current altitude being below the highest one, -1 meter, that's how we know we are going to deploy the parachute. So I'm running a free air toss. And free air toss is being structured by several independent tasks which can run in parallel. And when I was developing the code, I did it in several steps. Initially, the very first change was to send the altitude data just to a serial port. And I was doing this once every second. Then I needed to add a recording of the data so I can explore what's going on during the flight. So that task runs 100 times per second. And then I added live data to my application. And because that runs over the Bluetooth, I decided to run it 10 times per second. So what LLM decided to optimize for me, it saw that current altitude is used in one of these paths, so it only updates the altitude from these functions. While I was at home, I was always have live data running, which implies the current altitude would be updated 10 times per second. When I was outside, it was a little bit of rainy, so I did not have my computer with me. And also I was looking at the model anyway. So I have decided not to run live data. I did not run recording either, which implies I only had this task running. And as a result, the current altitude was updated just once per second, and obviously it just didn't have enough time to detect the top of the trajectory and deploy the parachute here. So that was an easy fix, but there was another issue which I did not see coming, and we'll talk about this at the end of this video. I updated the code and came up with a new idea how I can test it. I went to an elevator of my building. I basically went to the first floor, turned on the device, and went to the very last floor. And the expectation was for a model to deploy the parachute when we get to the last floor.
Hello. Going down.
At this point, it was time to stop testing indoors and move to real launches. This is the raw footage of those tests. Packing the parachute, checking the data on the computer, throwing the model and watching it land. And I also realized I still have a lot to learn about filming outside. So we have our ground. Alright, let's get it up in the air. Alright. On the screen, we need to arm it. Okay, we're at 11 meters. It's armed. And I'm ready to throw it. Let me see. And you can see the position for the servo being open. Alright, let's do a few more times. And we still have telemetry up and running. So we went basically 9 meters up. Great. I had 8 successful attempts to launch the model. Everything was great. But the last one was landed into a puddle. Not a big one, but still. And I decided to have one last shot for the camera. And here is what happened. Okay, we still have a data, but data is not moving, so probably something is off. Stop. Yep. Okay, actually it's not that bad. Alright. Now we can take a look what went wrong. And I actually have a few ideas. So first of all, we can see that the servo is in a closed position. Basically, the pin was looking this direction, and the servo is supposed to move this side to pull the pin with it. Saying that, we still have power, and all of this actually works just fine. Oh, and the servo just moved back to the original position. Let me do it one more time. Yep. So in general, stuff works. When I was testing the system on my laptop in the field, what I noticed after I got into water, the sensor started giving me bad data. So the lesson learned from this example: if I had a line of code which would trigger the parachute deployment, if the sensor gives me no data, all of this could be avoided. So it's going to be a lesson learned. And the last thing to take a look is how our electronics survived. So let's see. I'm going to disconnect it. Okay. This is great. One piece is a little bit screwed here. And obviously there are signs of an impact on these pins, but I don't think this is something I can quickly fix. Electronics seems alive, so we can use it on a different projects. In the next video, we're going to add a remote control to this parachute, so we can actually manage the flight path after the parachute is being deployed. Stay tuned for that, and thank you for watching.